Good afternoon, everyone. My name is Dr. Preeti Jawla, Assistant Professor, IIMT College of Engineering, Greater Noida. Today, I am going to discuss about the differential calculus. In the differential calculus, we are going to discuss a topic linear differential equations of nth order with constant coefficients. In this topic, linear differential equation, we are going to discuss about how we can solve the differential equations. First, we have to study about the differential equation. The equation of the form a naught dny upon dx to the power n plus a1 dn minus 1 y upon dx to the power n minus 1 plus a2 dn minus 2 y upon dx minus n minus 2 plus and so on a and y is equal to q. This type of equation is called linear differential equation with constant coefficients, where a naught, a1, a2, an are all constants. Because a1, a2, an are all constant. That's why we call linear differential equation with constant coefficients. And q is a function of x alone is called a linear differential equation of nth order with constant coefficients. Here, the operator d, the part d upon dx of the symbol dy over dx may be regarded as an operator. We write d upon dx is d, capital D. And similarly, d2y over dx2, capital D square, dn upon dxn is equal to capital Dn. The equation 1, which is described in previous slides, a naught dn of y upon dx2, we can write this equation in a naught d to the power n plus a1 d to the power n minus 1 plus a2 d to the power n minus 2 plus and so on a n minus 1 d plus a n y is equal to q. In short, we can write it f dy is equal to q. Here is a result. If y is equal to u is the complete solution of the equation f dy is equal to 0 and y is equal to v is a particular solution containing no arbitrary constants of the equation f dy is equal to q, then the complete solution of the equation becomes f dy is equal to q is y is equal to u plus v, where u is a complete solution and v is a particular solution. The part y is equal to u is called complementary function CF, and the part y is equal to v is called particular integral of equation f dy is equal to q, which is described in slide 1. The complete solution of equation 1 is given by y is equal to CF plus pi, where CF is complementary function and pi is particular integral. In order to solve f dy is equal to q, first we find to CF, that is complete solution of f dy is equal to 0. That means in this equation, the right hand side of the equation is equal to 0 and pi of f dy is equal to q. Complementary function CF. Consider the differential equation f dy is equal to q, that is equation number 1. CF is the solution of equation 1 when its right hand side member, that is q, is replaced by 0. As we have talked previously, the right hand side of the equation takes equal to 0, that is f dy is equal to 0. To find CF, first we obtain auxiliary equation of the given equation, then replace d by m and y by 1 in equation 2, then we get the auxiliary equation of the given equation. The general solution of equation 2 depends upon nature of the roots of the auxiliary equation. That means the nature of the roots. If real roots are real, then the solution is different. If roots are complex, then the CF is different. Let's we consider the case real roots. If m1, m2, m3, mn are n roots of auxiliary equation, following cases arise. Case 1, real and distinct roots. If roots m1, m2, m3, mn are real and distinct, then the solution of equation 1 is given as y equal to c1 e to the power m1x plus c2 e to the power m2x plus c3 e to the power m3x plus and so on cn e to the power mnx. Now the next case is when the real roots are real and repeated roots. If two roots m1, m2 are real and equal and remaining roots, that is two roots are real and the remaining roots are n minus 2 roots. M3, M4, Mn are all real and distinct, then the solution of equation 1 is given as y equal to c1 plus c2x into e to the power m1x plus c3 m3x plus c4 e to the power m4mx and so on cn e to the power mnx. Let's consider an example. For example, solve d cube y over dx cube minus 7 dy over dx minus 6y is equal to 0. Now the solution of the given example. First, we have to consider the auxiliary equation of the given question. M cube minus 7m minus 6x is equal to 0. First, we have to calculate the roots of the auxiliary equations. The roots of given question is m equal to -1, -2, and 3. The three roots are real and distinct. The roots are real and distinct, that is complementary function of given problem is equal to c1 e to the power minus x plus c2 e to the power minus 2x plus c3 e to the power 3x. The particular integral of the given problem is 0 because the right hand side of the given problem is equal to 0. That is, there is no q. That's why the particular integral of the given problem is equal to 0. Hence, the complete solution is y equal to cf plus pi. That is equal to c1 e to the power minus x plus c2 e to the power minus 2x plus c3 e to the power 3x. Let's consider another example. First, consider the auxiliary equation of the given problem. M cube minus 5m square plus 8m minus 4 is equal to 0. Calculate the roots of this problem. M equal to 1, 2, 2. Here two roots are equal. The two roots are real and distinct, but the second root m equal to 2 is repeated twice. Then the solution of the given problem is y equal to c1 e to the power x plus c2 c3x into e to the power 2x. Now let's consider the another case. When two roots of the auxiliary equation are imaginary, let m1 is equal to alpha plus iota beta and m2 equal to alpha minus iota beta. That is, roots are complex. Then the CF of given problem is e to the power alpha x c1 cos beta x plus c2 sin beta x plus c3 m3x plus and so on cn e to the power mnx. Case 4, when roots of auxiliary equation are repeated imaginary, that is, the roots m1 m2 equals to alpha plus iota beta and m3 m4 is equal to alpha minus iota beta. Rest of the roots are real and distinct. CF is equal to e to the power alpha x c1 plus c2x cos beta x plus c3 plus c4x sin beta x. Because two roots are equal, m1 is equal to m2 and m3 is equal to m4. That's why we have take c1 plus c2x and c3 plus c4x plus c5 e to the power m3 m5x plus so on cn e to the power mnx. Now the case 5, when roots of auxiliary equation are irrational, let m1 is equal to alpha plus root beta and m2 equal to alpha minus root beta. Then the complementary function of the problem is e to the power alpha x c1 cos hyperbolic root beta x plus c2 sin hyperbolic root beta x plus c3 m3x plus so on cn e to the power mnx. Now let's consider the example. First we have to consider calculate the auxiliary equation of the given problem. M4 plus 8 m square plus 16 is equal to 0. The roots are m equal to plus minus 2 iota and plus minus 2 iota. The pair of roots is imaginary and repeated twice with alpha is 0 because the first part, a real part of the root is 0. Imaginary part is 2 iota. So beta is equal to 2, hence the solution is y equal to e to the power 0 x c1 plus c2x because roots are repeated cos 2x plus c3 plus c4x into sin 2x. Because e to the power 0x, that means is equal to 1, then y is equal to c1 plus c2x cos 2x plus c3 plus c4x sin 2x. Let's consider another example. Solve d square plus 1 whole cube d square plus d plus 1 whole square y is equal to 0. The auxiliary equation of the problem is m square plus 1 whole cube m square plus m plus 1 whole square is equal to 0. Now we calculate the root of the given equation. M square plus 1 is equal to 0. That means m equal to plus minus iota. M square plus m plus 1 is equal to 0. M equal to minus 1 plus minus iota root 3 by 2. Both pair of roots are imaginary, that is because there is iota, and first pair is repeated thrice with alpha equal to 0, beta equal to 1, and second pair is repeated twice with alpha equal to minus 1 by 2. If we calculate the real part of this m, we got the alpha equal to minus 1 by 2 and beta is equal to root 3 by 2. Hence, the solution of the Grimm problem is y is equal to e to the power 0x. The roots are repeated thrice. That's why c1 plus c2x plus c3x square cos x plus c4 plus c5x plus c6x square sin x from the second root plus e to the power minus x by 2 because the alpha value of alpha is equal to minus 1 by 2. So take v to the power minus x by 2 bracket c1 plus c8x cos root 3 by 2 x plus c9 plus c10 x sine root 3 by 2 x. Now let's a summary of CF according to the auxiliary equations. If the root of auxiliary equation one real root alpha, then the CF function is look like C1 e to the power alpha 1x. Two real and differential roots alpha 1 and alpha 2, C1 e to the power alpha 1x, C2 e to the power alpha 2x. Two real and equal roots alpha 1 and alpha 2 are equal. C1 plus C2x e to the power alpha 1x. Three real and equal roots alpha 1, alpha 2, alpha 3, C1 plus C2x plus C3x square e to the power alpha 1x. One pair of imaginary roots alpha plus iota beta, C1 cos beta x plus C2 sin beta x into e to the power alpha x. If two pairs of equal imaginary roots alpha plus iota beta and alpha plus iota beta, in this case e to the power alpha x c1 plus c2x cos beta x plus c3 plus c4x sin beta x. Rules for finding pi function. Pi, that means particular integral of the given problem. The solution made from two parts, CF and plus pi. The CF is complementary function and pi is particular integral. Consider the differential equation, general differential equation, dn plus a1 dn minus 1 plus a2 dn minus 2 plus and so on a to the power a n minus 1 d plus a n y is equal to q. If we find particular integral, we have to note that what is the value of q. The particular integral is dependent upon q function. The general equation is can be written as f dy is equal to q, pi is equal to 1 upon f dq. First, we consider when the value of q is exponential. That is, the q is equal to e to the power ax or the form of e to the power ax plus b. In that case, the pi function is equal to 1 upon fa e to the power ax plus b when fa is not equal to 0. The pi is equal to 1 upon fa a to the power ax plus b if fa is not equal to. If fa is equal to 0, then we have take another case, another term. This case is considered as case of failure. If fa is equal to, then 1 upon fd e to the power ax is equal to x into 1 upon f dash a. That means first derivative of fd, then we substitute the value of a from e to the power exponential term where f dash a is not equal to 0. If f dash is equal to 0, then repeating the above process again, 1 upon f d e to the power ax plus b is equal to x into x 1 upon f double dash a e to the power ax plus b where f dash double dash is not equal to 0. If again we get the f double dash is equal to 0, then repeat the above process same and so on. Let's consider another example. Solve 2d cube y upon dx cube minus d2y over dx square plus 4dy over dx minus 2y is equal to e to the power x. Here, as we can see that there is a value of q is e to the power x. That means q is an exponential function. First, we have to find the CF of the given problem. For find CF, we have to find auxiliary equation of the given problem. The auxiliary equation of the given problem is 2m cube minus m square plus 4m minus 2 is equal to 0. Then we find the roots of the given auxiliary equation. M is equal to 1 by 2, that means real root, plus minus root 2 iota, that means imaginary roots. That means we got the three roots, one is real and two is imaginary. Then the CF is equal to C1 plus e to the power x by 2 plus C2 cos root 2x plus C3 sine root 3x. Then next step is find the value of pi function. For pi is equal to 1 upon 2d cube, yeah, that means fd is d equation of the given problem, 2d cube minus d square plus 4d minus 2 into e to the power x. As we, if we compare the e to the power x is the given function, that is e to the power ax, we got the value of a is equal to 1. Then we substitute the value e is equal to 1. Then 1 upon 2 1 cube minus 1 square plus 4 1 minus 2 e to the power x. Then after solving this term, we got 1 by 3 e to the power x. Hence, the complete solution of the given problem is y equal to CF plus PI. CF, that means this term, and PI, this term. PI is 1 by 3 e to the power x, and CF is C1 e to the power x by 2 plus C2 cos root 2x plus C3 sine root 2x, and then value of pi 1 by 3 e to the power x. This is the complete solution of the given problem, where C1, C2, C3 are arbitrary constants of integration. Now the next case, when q is sine ax plus b or cos ax plus b, that means the q function is sine function or cos function. In this case, we calculate the pi by a given method. 1 upon f d square sine ax plus b is equal to 1 upon f of minus a square. That means in place of d square, we substitute the value of minus a square in the given d equation. Sine ax plus b provided f of minus a square is not equal to 0. That is, if this condition have to check if f of minus a is not square is not equal to should be 0. Next, in case of cos, 1 upon f d square cos ax plus b is equal to 1 upon f of minus a square cos ax plus b, provided f of minus a square is not equal to 0. Now the steps when q is equal to sine x or cos x plus b, how we can find the pi method? Replace d square by minus a square, d4 by a4, d6 by minus of a6. Remember the sign of minus, d8 by a8, and so on. By doing so, the following possibilities arise. If denominator reduced to a constant, it will be final step in finding pi. If the denominator reduced into d only, that means the differentiation term, we are then only to integrate the given function. If denominator reduced to a factor of the form of alpha d plus beta, then we operate by its conjugate, alpha d minus beta, on both numerator and denominator from left hand side, such as alpha d minus beta into 1 upon alpha d plus beta sine ax plus b. By doing so, denominator will become alpha square d square minus beta square, which in turn reduce to a constant by replacing by d square. As we know, the we substitute the value of d square by minus a square. And now we operate sine ax plus b by alpha d minus beta, and consequently find the required particular integral. Now let's consider an example. Solve the following differential equation: d square plus 4y is equal to sine 3x plus cos 2x. In this case question, first we have to find the auxiliary equation, which will be m square plus 4, and the roots are imaginary, plus minus 2 iota. Then the CF is C1 cos 2x plus C2 sin 2x. In here, value of alpha is equal to 0 because the roots are plus minus 2 iota. Then the final CF is C1 C2 cos 2x plus C2 sin 2x. Now next proceed for PI. PI is equal to 1 upon d square plus 4 sin 3x plus 1 upon d square plus 4 cos 2x, because we have two functions. The first is sin 3x plus another is cos 2x. Here the value of a is, if we compare it with general term sin ax plus b, the value of a is 3. Then we replace d square by minus of a square. Remember the sign minus a square. The value of a is 3. Then we replace d square by minus of 3 square. 3 square, that means minus 9. Plus 4 sine 3x plus x 1 upon 2d cos 2x minus 1 upon 5 sine 3x x by 2 sine 2x by 2, which is equal to minus of 1 upon 5 sine 3x plus x by 4 sine 2x. Then the complete solution of the given problem is y is equal to cf plus pi is equal to c1 cos 2x plus c2 sine 2x minus 1 upon 5 sine 3x plus x by 4 sine 2x. Now let's consider another case when q is equal to x to the power m, when q is a function of x in type of x to the power m, m being a positive integer. Then how we can find the pi of the q? Steps: take out the lowest degree term from FD2 to make the first term unity so that the binomial theorem of a negative index is applicable. The remaining factor will be of the form 1 plus phi d or 1 minus phi d. Take this factor in the numerator. It takes the form of 1 plus phi d minus 1 or 1 minus phi d minus 1. Then we expand it by binomial theorem, expand it in ascending powers of d, so as far as the term containing d to the power m. Since dm plus 1 x to the power m is equal to 0, that's why we consider only d to the power m. dm plus 2 is x to the power m 0, and so on. Operator on x to the power m term by term. Now take the example, find the pi of y double dash minus 6y dash plus 9y is equal to 2x square minus x plus 3. Here we have to find only pi function. That is pi is equal to 1 upon d square minus 6d plus 9 2x square minus x plus 3, which is d square minus 6d plus 9 is whole square of d minus 3. 1 upon d minus 3 whole square, 2x square minus x plus 3. Now we common the term 3, then it becomes 1 upon 9, 1 minus d by 3 to the power minus 2, 2x square minus x plus 3. If we expand 1 minus d upon 3 minus 2 by binomial theorem, then we get the 1 upon 9, 1 plus 2d upon 3 plus 3d square upon 9 plus and so on, 2x square minus 3 minus x plus 3. Leaving the higher powers of the d, because the maximum power of x is 2. 1 upon 9, 1 plus 2d upon 3 plus d square by 3, 2x square minus x plus 3. Then we multiply both the terms. Then we get 1 upon 9, 2x square minus x plus 3, 2 by 3 d. D, that means differentiation of given function. D, differentiation of this function is 2 into 2, 4x minus x, differentiation of x is equal to 1, differentiation of 3 is equal to that. That means we get 4x minus 1 and d square by 3, 1 upon 3, d square of this function, 2x square minus x plus 3, d square of this function is 4. Then after solving this equation, then we get 1 upon 9, 2x square plus 5x by 3x plus 11 by 3, which is the particular integral of the given problem. Now let's consider another case when q is equal to e to the power ax b, where v is a function of x. Q is equal to e to the power ax, that means an exponential function, into v is a function of x. Then the pi is equal to 1 upon d e to the power ax, v is equal to e to the power ax 1 upon f of d plus a v. That means we replace d by d plus a. Now take the example, find the complete solution of the d square y dx square minus 3 dy over dx plus 2y is equal to x e to the power 3x plus sine 2x. Now the complementary function of the given problem is c1 e to the power x plus c2 e to the power 2x. Then now the next step is find the pi. Pi is equal to 1 upon d square minus 3d plus 2. The given problem is x e to the power 3x plus sine 2x. The value of q is given problem is x e to the power 3x plus sine 2x. Now the next step is 1 upon d square minus 3d plus 2 e to the power 3x into x plus another function is 1 upon d square minus 3d plus 2 sine 2x. Here we apply the method of sine function and cos function. Here we apply the method of case 4, that is when q is equal to e to the power ax into v, where v is the function of x. In this case, e to the power ax, and we replace d by d plus 3 because here the value of a is 3. Then we replace d by d plus 3 whole square minus 3 into d plus 3 plus 2 x plus here in this case the d square is replaced by minus a square. Here the value of a is 2. 1 upon minus 4 minus 3d plus 2 sine 2x. Then we solve, after solving this we got e to the power 3x 1 upon d square plus 2d plus 2x plus 1 upon minus 3d minus 2 sine 2x. Another next step is e to the power 3x 1 upon 2 1 plus 3d plus d square by 2x minus now 1 upon 9d square minus 4 sine 2x. 3 next step is 3 e to the power 3x by 2, taking the numerator 1 plus 3d plus d square by 2 minus 1 x 3d minus 2 minus 40 sine 2x, because the d square replaced by minus of 4. So 9 into minus 4 minus 4. Now the expand it by binomial theorem, then we get e to the power 3x upon 2 1 minus 3 divided 2x plus 1 upon 46 cos 3 2x, because we differentiate when we multiply 3d minus 2 into sine 2x, we get 3d sine 2x. 3d d means differentiation of sine 2x minus 2 sine 2x, differentiation of sine 2x cos 2x 2 into so 6 cos 2x minus 2 sine 2x. 1 minus 3 divided 2 multiply x e to the power 3x upon 2x minus 3 by 2 plus 1 upon 23 cos 2x minus sine 2x. Then the complete solution becomes y is equal to cf plus pi, where cf is equal to c1 e to the power x plus c2 e to the power 2x. Then the complete solution is c1 e to the power x plus c2 e to the power 2x plus e to the power 3x by 2 into x minus 3 by 2 plus 1 upon 23 cos 2x minus sine 2x, where c1 c2 are arbitrary constants of integration. Now let's consider another case when q is a function of x, which is defined which is not defined in previous cases. Remember the following formula: 1 upon d minus alpha q is equal to e to the power alpha x integration of e to the power minus alpha x q dx. Another is 1 upon d plus alpha q is equal to e to the power minus alpha x integration of e to the power alpha x q dx. For this case, let's we consider an example. Find the complete solution of d square plus a square y is equal to second is. First, we consider the auxiliary equation of the given problem. The auxiliary equation of the given problem is m square plus a square is equal to 0. That means m is equal to plus minus a iota. Here, value of alpha is 0 because there is no real term, only imaginary terms. Alpha plus alpha m is equal to plus minus a iota. Then this case cf is equal to c1 cos ax and c2 sin ax. Then the pi is equal to 1 upon d square plus a square second s. First we factorize the denominator, d square plus a square 1 upon d minus iota a plus d minus d plus iota a second s is equal to 1 upon 2. Then we do the partial fraction of this function, 1 upon 2 iota a 1 upon d minus iota a minus 1 upon d plus iota a sec x. 1 upon the solving multiplying sec ax into this function, then we get 1 upon 2 ia 1 upon d minus iota a sec ax and minus 1 upon d plus iota a sec ax is equal to, here we consider this part is first part is p1 and second part is p2. where P1 is equal to 1 upon D minus iota A sec AX, which is now applying this formula, which is reading previously, is equal to e to the power iota AX integration of e to the power minus iota AX sec AX dx. After solving this, e to the power iota AX, expanding e to the power minus iota x in terms of cos and sine, cos ax minus iota sine ax sec ax dx. Then we write e to the power iota ax integration of 1 minus iota 10 ax. When we multiply sec ax, as we know that the sec ax is equal to 1 upon of cos ax, then we multiply the term in this term cos ax minus iota sine ax, then we get 1 minus iota 10 ax dx is equal to e to the power iota ax bracket x plus iota log. When you integrate this term, then we get the x plus iota log cos ax upon a. Now we calculate the part 2, that is P2. P2 is 1 upon d plus iota a sec ax is equal to e to the power minus iota ax bracket x minus iota log cos ax upon a. Now the complete PI is 1 upon 2 iota a P1 minus P2. Then we can write the here value 1 upon 2 iota a e to the power iota x plus iota cos log cos ax upon a minus e to the power minus iota x minus iota log cos ax upon a. This value of P1 and this is the P2. 1 upon 2 iota a into x e to the power iota ax minus e to the power minus iota x plus iota log cos ax upon a e to the power iota ax plus e to the power minus iota ax. We simplify this term, then we get 1 upon 2 iota a bracket 2 iota x sine ax plus 1 upon iota upon a log cos ax. 2 cos ax is equal to 1 upon a x sine ax plus 1 upon a cos ax log cos ax. Hence, the complete solution of the given problem is CF plus PI, when CF is where C1 cos AX plus C2 sin AX, and the PI is equal to 1 upon AX sin AX plus 1 upon A cos AX log cos AX, where C1 and C2 are arbitrary constants of integration. And we can study about the another form of linear differential equations, homogeneous linear differential equation, which is also called Euler-Cauchy equation. An equation of the form x to the power n dn y upon dx and plus a1 x to the power n minus 1 d n minus 1 y upon dx n minus 1 plus a2 x to the power n minus 2 d n minus 2y upon dx n minus 2 plus and so on, a n minus 1 x dy over dx plus a n y is equal to k. This type of equation is called homogeneous linear equation, where a1 ai's are constant and q is the function of x, which is also called a Cauchy's homogeneous linear equation differential equation. Such equations can be reduced to a linear differential equation with constant coefficients by the substitution of x to the x equal to e to the power z or z equal to log x. Steps for solution: put x equal to e to the power z so that z equal to log x, then and let d is equal to d over dz, that is the operator d is equal to d upon dz. Replace x d by dx by capital D, x square d square upon dx square by d into d minus 1, x cube d cube upon dx cube by d into d minus 1 d minus 2 and so on. By doing so, this type of equation reduces to linear differential equation with constant coefficients, which is then solved as before. Let's take an example. X square d square y upon dx square minus 2x dy over dx minus 4y is equal to x to the power 4. Now, for this equation, this type of equation is called a homogeneous differential equation. First, we have to do a substitution, which is x equal to e to the power z, and operator d is equal to d upon dz. X dy dx is equal to dy x squared d2y over dx2 is equal to d into d minus 1y in 1, which is given equation. D minus d into d minus 1y is minus 2 dy minus 4y is equal to e to the power 4z, or d square minus 3d minus 4y is equal to, after simplifying this term, we get d square minus 3d minus 4y is equal to e to the power 4z. For this equation, we have to find auxiliary equation of this equation. The auxiliary equation is m square minus 3m minus 4. Then we calculate the roots of m. M is equal to minus 1 and 4. That means roots are real and distinct. Then the CF is C1 e to the power minus z plus C2 e to the power 4z. Then we calculate the PI of the given problem, because the Q function is e to the power 4z. That means Q is exponential. We can apply the case 1 for PI method, 1 upon d square minus 3d minus 4 e to the power 4z. Here d is replaced by e to the power 4z. As we compare e to the power 4z, that means the value of a is 4. So here d square is replaced by sorry, d is replaced by 4. That means d square minus 3d minus 4. As we put the value of 4, we get the f of a is equal to 0. That is f of 4 is equal to 0. That means root failure, case of failure. Then we apply the another step, z into 1 upon 2d minus 1. That means differentiation of d square minus 3d minus 4, which is 2d minus 3 into e to the power 4z. Then we apply same method, e to the power 4z. The value of a is 4. In place of d, we put value 4. So z 1 upon 2, 4 minus 3 e to the power 4z is equal to z e to the power 4z upon 5. Thus, the complete solution of given equation is given by CF plus PI. The CF is e to C1 e to the power minus z plus C2 e to the power 4z, and PI is z e to the power 4z upon 5. Then again we transform the equation in x, as we put the substitution x equal to e to the power z. Then final solution is y equal to C1x plus C2 x to the power 4 plus 1 upon 5 x to the power 4 log x. Okay, thank you.